Okay, hello. I am recapping and moving along with our notes today. I am trying to get you brought up to speed because it's been a little bit of a time crunch with these 40-minute classes as we start. So these notes are on Canvas, okay, number one. So I'm just going to talk you through it a little bit for time's sake, so it's not a 45 or hour long video. If you want to pause and slow down, you can, and do it on your blank paper. Just try to kind of follow along with what we're doing here that's already sort of completed, and then I'll talk about it as we go through. So this was the example that we just kind of grazed on in class this year with the cereal boxes. We more did the bottle flipping. Okay, skewed right has to be independent, a fixed number of outcomes. We use the acronym BINS, that it's binary, independent, the number of successes, and that you get a success on the first one. They're typically skewed right, and you have a success or a failure, and then we did all this fun calculator stuff then the next day. So this was geometric distributions, okay? Again, these we were pretty caught up on, and the mean is 1 over p, and we call this a probability density function. Okay, did a couple on your own, and then I think that's where we wrapped up on Friday. Okay, then we got into these Bernoulli trials just ever so slightly, and some examples, head, tail, 6, not 6. This is sort of the key, that you have a success or a failure. So you still need to have a success or a failure. Okay. Only 2 outcomes. So in the StatsMedic thing, we sort of use that BINS acronym, binary, independent, that number of success, the sample size, and the success rates. Okay, those are kind of some key ingredients to those. Then we get into this law of large numbers. Okay, a little bit of a review with when it feels like we're kind of coming back to some normal stuff with the calculator. Okay, so if the sample contains no more than 10% of the total population size, then the probabilities don't change enough to matter. So again, thinking of millions of cereal boxes on the shelf, and you are pulling one, it's really not non-replacement if these conditions are met. So if the sample size, N is the sample size and capital N is the population size. So as long as the sample size is less than 10% of the population size, you're good to go. So that would kind of bypass that without replacement condition. Recall using Normalcdf on your calculator. If you forgot where that was, always you can always look it up. Ask second distribution, Normalcdf is here. A little bit later, we're going to get down to this binomial PDF and CDF. PDF is when you want to know the exact number at that point. So it's the probability of like 2 rolls, or, you know, guessing 2 questions correct on my test. And CDF is up to and including that point or less than that point. Okay, so think of CDF as a cumulative and PDF is the probability at that point. All right, so recalling Normalcdf, so you're looking for the cumulative density function under that curve. It's always the left bound, the upper bound, the mean, the standard deviation. So the last chapter we started calculating our own standard deviation and our own mean with the expected value. So kind of a lot going on in chapter 15 and now 16. So geometric PDF is the number of trials for the first success. Geometric CDF is the probability of those successes. Binomial is a shade different, which we're kind of keep talking about. So PDF is the probability density function at that point, and CDF is the cumulative density function. You're using your calculator for the shortcuts. It's really important that you distinguish which one you need to use. So if we want to get our tiger card on the 8th try, the PDF of the 1/3, remember that was the success, 8th try is that. Check for not seeing a success for up to, we're just changing this a little bit, 7 trials, you've got the cumulative density function. Okay. All right, so now we're kind of getting into another situation with binomial distribution. So exactly 2 successes versus first. So the fixed number of trials versus waiting for success. Geometric, that's the main distinguish, that you're waiting for that success to happen. Okay, so the conditions required for geometric distributions are required with binomial distributions as well. 2 outcomes, independent, constant p, and failure. All right, for binomial distributions, there's a fixed number of trials, whereas geometric, you're waiting for that first success. So it's sort of pending, if you will. All right, so if you looked for some of the different situations of how that could happen, then your calculator kind of makes a little bit more sense, because we don't want to do all this by hand, right? So we've done a couple of these with Statsmetric examples where we've written them out, or in class, if I was here today, you know, we could kind of space this out. But over time, you don't want to do that. You want to eventually get to your calculator, all right? But you want to understand what that means, okay? So you kind of have, for this one particular outcome, 2 successes, all these failures, then you've got those 2 successes, all these failures. That's the probability. But there's so many possible arrangements. Okay, so how do you determine to solve that original problem? So we need to know how many different combinations there are. So now you're going to get into your combination function on your calculator. Okay, yes, there's a formula, n factorial. Remember, that means you take like a number times the one below it times the one below it, da-da-da-da-da-da. Eventually they kind of cancel out, times r factorial over n minus r factorial. Again, we used to do these a lot when we were in advanced algebra, but math 1, 2, 3 is a little bit not the same. This is way easier, okay, to use a combination on your calculator. All right, so think about like the ways that you can win a basketball game if you're shooting free throws or if you tie it up. So if you're shooting 3 free throws, you've got make, miss, make, miss, make. So there's all these combinations to tie it up, to go into overtime, to lose. So there's sometimes more than one way, you know, you could miss the first 2, make the third, make the first, miss the next 2. So there's different combinations that would have the same outcome. So that's why we have to account for all of those possibilities. So that on your calculator, which if you haven't seen it in a while, is math over to probability. Okay, and there's your NCR. So remember, you have to put the number in first, hit this math over to probability, and then R is the number of successes. So this is how many trials. So I want 2 shots made out of the 3. I want to score, 3 correct out of my 5-question quiz, what have you. All right, so that is called the binomial coefficient. So that can be read as n choose r. So back to tiger, we're looking for the probability of getting exactly 2 tiger cards in 8 trials. So we know that the probability of this, one way for this to happen would be that we just talked about, 2 successes, 6 failures. But once we know how many different ways that 2 successes and 6 failures can occur in 8 trials, we can simply multiply the probability we just found by that value. okay? So we'll take how many ways that can occur. All right, so you have to go to the home screen. You want 8 trials, and you want 2 successes, okay? So then you'll get your 28. So that's how many combinations that you could get that. So that's where, I know that we had a working day the other day, and a couple of you were asking me where we get that number in front. So you have to enter that all at once. So 8, choose 2, times 1/3 squared, 2/3 to the 6th to get that value. All right. I'm kind of, again, I know I'm going fast. I'm just kind of talking about these notes. You can pause them. You can look on Canvas. If you're understanding them just without any video, awesome. But suppose the manufacturer makes 50,000 boxes per week. What's the probability that at least 16,800 of them contain a tiger card? So on the calculator, that would be 1/3 times that number. All right, 50,000 less that number times that combination. All righty. So that would get an overflow. Can we do it by hand? So that's the binomial coefficient formula, so to speak. All right, so from your reading, recall that the mean and the standard deviation of the binomial distributions are, the mean is 8 times 1/3, so 8/3, number times p. Oh, this was freezing. I hope this is still going. And then the standard deviation is the square root of NPQ. All right, again, this is in your reading. This is on your formula cards. This is, I know it's a lot of formulas. You always kind of want to keep in track what those numbers are. Even when you go to your calculator, you'll notice that once you hit like a second distribution, BDF, CDF, it'll say things like number of trials, what's the P value, what's the X value. Okay, so P is your success. 1 minus P would be your failure. X value is typically how many, like your winner, so to speak. Okay. All right. So if the number of trials is so large that your calculator runs out of steam or memory, we can rely on the histogram of any binomial distribution is normal. So if a close approximation will suffice, we can use the normal curve to get areas under that to approximate that binomial probability. That's why we're kind of getting back into that normal curve type of thing. Whee! All right, how large does n have to be? So the condition for using a normal curve in order to approximate a binomial probability is the success-failure condition. It's approximately normal if we expect at least 10 successes and 10 failures. And you must show the math. AP Test loves you to show this. So the success-failure condition, we have to check for normalcy, check for if we can use not only a binomial, but is it under normal conditions. So if NP is greater than or equal to 10, and n times 1 minus p, remember that's number of failures, is greater than or equal to 10, then we can move forward with our normal. Okay, just a couple examples of some of the math histograms. Okay, this is kind of a lot of theory. Okay, so although our authors do not include this in the textbook, most sources do. So you do want to be able to know some of the theory behind that. You always have to define your variables and determine if you can not only use a binomial, but use a normal curve. So kind of a lot going on there as far as proof. So a lot of math here. So I'm going to let you pause the video if you want. Basically, find the probability of 12 heads by finding the area of the rectangle that starts at 11.5 and ends at 12.5. Alrighty, so again, don't necessarily have to memorize these. They are on your formula card, but you have to know when to use what. Alright, so you've got your binomial notation, your normal model notation. So because it becomes a normal model, you're going to use Normalcdf, cumulative density function. Lower bound, upper bound, mean, standard deviation. Okay, binomial notation, we're going to take the successes of 12 out of 50. So think of it as 12, choose 50. 50, choose 12 rather. We want 12 successes, and that would leave us 38 failures. So kind of a lot to kind of wrap it all up together here in chapter 16. All right, I may as well just finish. Again, you can pause. We'll talk a lot tomorrow and the next day. Our test is Thursday. Okay, so find the probability of at least 12 heads. So that is 12 or more. So we have to change the binomial distribution to the normal for our approximation. Alrighty, we'll use the same values in the normal. Then we have to convert to a z-score. So we need the area under the curve from 11.5 to the right. Boop. All right, so I know that some of you are like, oh, this is all coming back. It is. So this is a website you can access. It's not live because your notes are on paper, but you can type that in and you can see that phenomenon. Yahoo. Okay, we're going to hop over this. I might have time for it before our test. And this last one is success failure. You always have to show this. So you just get in the habit of showing your success failure condition, things that are normal. You want to label your normal curve with your mean and your standard deviation. If you have to compute it, whether it's one of these formula or the expected value in chapter 15, make sure you do that. And we're done. Okay, so I know that was just like less than 20 minutes. It's a 40-minute class, so I hope you can have enough time to pause and work through your calculator. I'm noticing a lot of you are just kind of like hanging out. Unless you are yourself going through the process and knowing where things are, it's going to kind of continue to be a struggle. So come join us with your graphing calculator, work on your homework, and we'll have a couple days to review for the test. Have a great day.